Muy bien, vamos a dar por comenzada la defensa de tesis de doctorado de Lucía Gonzalez, que contó con la dirección de la doctora Flavia Bonomo y como consejero de estudios actuó el doctor Javier Marenco. Nos acompañan en la transmisión virtual Paloma Tomé de Lima, Dimitros Tílicos y Sergio Cabello, que son los jurados de la defensa. Por las dudas, les comento a los tres la modalidad. Carolina va a hacer su exposición de los temas, los resultados. Luego viene una etapa de preguntas que es tanto tiempo como ustedes necesiten para consultar todas las dudas que tengan al respecto de la tesis. Una vez que fueron evacuadas absolutamente todas las dudas de parte del jurado, pasamos a una etapa de deliberación que es privada. Sí, para eso vamos a hacer en el Zoom una sala, una breakout room, para que puedan ingresar los miembros del jurado, solamente los miembros del jurado, más una pequeña guía inicial de mi parte, como para dar las notas y explicar cómo funciona nuestro sistema por las dudas. Eso no se transmite, no está en YouTube. Una vez que ustedes deliberen, salen de esta sala de privada y alguno de los tres tendrá que darle la nota a Carolina. Y después de eso, bueno, continúa el proceso. Una vez que termina la defensa, no se requiere de ustedes ninguna firma, ningún acta, ningún documento. Con su participación en esta defensa y la deliberación y la nota, alcanza y termina su responsabilidad. Bueno, habiendo dado las instrucciones, Carolina, mucha suerte y, como dicen, el aire es tuyo.
Bueno, muchas gracias. Esta presentación a pedido del jurado va a ser en inglés, así que a partir de ahora todo en inglés. Hello everyone. Thank you for joining this transmission and for those who came here personally. So I'm going to talk about what I did for my PhD thesis. So the topic is locally checkable problems parameterized by treewidth, clique-width, and mim-width. So I'm going to start talking about three problems that I hope you are all familiar with. So I have k-coloring, minimum dominating set, and maximum independent set. These three problems, which may seem completely different at first sight, actually, they have two characteristics in common. So the first one is that these problems are what we call partitioning or coloring problems. So we have to classify the vertices into different categories or colors. In the case of k-coloring, this is clear. We have the colors. In the case of these two problems, we can consider that we have two colors. So the color that represents the vertices in the set and another color for the other vertices. The other characteristic that they have in common is that there's some local property that needs to be satisfied for every vertex. So a local property is a property that depends only on the vertex and its neighbors. So for example, for k-coloring, we have that every vertex has to receive a color different to its neighbors. For minimum dominating set, every vertex, it's either in the set or has at least one neighbor in the set. And for maximum independent set, if a vertex is in the set, then none of its neighbors is in the set. So all these problems, not only these three, there are infinitely many more that share these two characteristics of being coloring problems that must satisfy a local property for a vertex are what we call locally checkable problems. So why do we study these problems? Well, first of all, because many well-known graph problems are actually locally checkable and they have applications in real life. We have, for example, assigning resources or placing facilities. And because of this, it's interesting that we are interested in solving them efficiently. And with this, there are some questions that arise. So first, for which graph classes can we solve these problems efficiently and how? So which algorithms can we give for that? And as it happens, there are some graph classes for which the algorithms are actually quite similar. And so it is natural to wonder if we can generalize these ideas. And well, in this direction, there's a lot of work here. There's just a few examples. For instance, the first one, LCP problems. It's a very particular subset of locally checkable problems that through different publications, it was proved that it can be solved in polynomial time for many different graph classes. Here we have LCC and ECC problems, which are a bit more than just locally checkable, but they were solved for less graph classes. And then the last two examples, so we have Purcell's theorem and ANC and logic. In these two, the idea is that if we can model a problem in a particular logic, then the results in these publications say that we can solve it efficiently for some concrete graph classes. And well, why did we continue this study? There's so many work already done. Well, there are some particular locally checkable problems that we were interested in solving, and that either we couldn't model them in any of these frameworks, or we wanted to solve them for more graph classes. So that's why we continued with this study, but we took a different approach. So instead of defining a large set of problems and then showing for which graph classes we can solve these problems, we did the other way around. We defined the whole set of locally checkable problems. We defined the framework for all these problems. And then for a given graph class, we will see how far can we go with the problems. How many problems can we solve for those graph classes in polynomial time. So, well, as I said, we abstract the notion of locally checkable problems into a new framework so that every problem that we understand intuitively that is locally checkable can be modeled here. And our goal is to try to answer this question: what makes these problems easy or hard in terms of solving them efficiently? So we will classify them according to different restrictions on the local property of the problem and the set of colors that we want to assign to the vertices. In particular, we will study the complexity of these problems in terms of different width parameters, which are called treewidth, clique-width, and mim-width, and I will talk about them later. For this end, on one hand, we develop efficient algorithms under some particular set of restrictions, and we show that we cannot simply get rid of these restrictions, because if we do, then we find some hard problems in those groups. The results that we obtain generalize those of some of the previous frameworks, and we also applied our results to a large set of problems for which their complexity on these graph classes was not known. And lastly, we also presented not only exact algorithms, as I said before, but also approximation algorithms for some of these problems on a graph class called the planar graphs. So now allow me to start already talking about the topics of this thesis. So first of all, what is this parameterized complexity that we mentioned here in the title of the thesis? So a parameterized problem is considering to have an input in two parts. So on one hand, we have the main input, which in our case, it's usually just a graph. Then we have a parameter. So this parameter can be something, for example, concrete of the problem. So it can be the number of colors or the size of the solution, or it can also be something that depends on the graph. It can be the maximum diameter, the diameter or the maximum degree, or more, which are the ones that I will present later. And the idea is to express the complexity of the problems in terms not only on the size of the main input as it is usual, but also on terms of this parameter. We want to make this parameter explicit in the complexity analysis. So we will, according to the kind of complexity that we obtain, we will classify the problems in different categories. First, we have the set of FPT problems, whose complexity is like this. We have some function on K multiplied by the size of the main input to the power of some constant. Yeah, this constant, of course, unrelated to the parameter K or the input. Then we have the set of XP problems, where, well, the only difference is that here in the exponent, we have some function on K. Notice first that XP, of course, contains FPT. And secondly, and most importantly, notice that if we fix the value of k, then these complexities are polynomial on the size of the mim-width. However, we still prefer FPT because the impact of this parameter in the complexity is less in FPT than XP, because here it's on the X1. Anyway, these two cases are still preferred to the third set of problems, which is par-NP hard. So these problems are NP hard even for fixed values of k. So now let me tell you about the parameters that we will use for the parameterized complexity. So we use what is within the set of width parameters. So intuitively, a width parameter expresses how complex is a graph. For example, the parameter called treewidth expresses somehow how far is the graph from being a tree. So trees have treewidth 1, but a complete graph of n vertices has treewidth -1. Now, the definition of the other two, I will not give it now due to lack of time. But what we should know is that any graph class that has treewidth bounded by some constant also has clique-width bounded by some constant. And all these classes also have mim-width bounded by some constant. But, well, there are, of course, some graph classes, for example, integral graph, which have mim-width 1, but unbounded clique-width, and also graph classes of bounded clique-width that have unbounded 3. And well, here I just mentioned a few very well-known graph classes so that we all have some big panorama of the situation. Why did we choose these parameters? Well, first of all, because we can see they include many well-known graph classes. They were largely studied as well before us. And also because in particular, these three parameters have some tree structure associated to them, which is very useful for applying dynamic programming. This allows us to traverse the graph in a very structured way, very controlled way with nice properties, so we can apply dynamic programming. So the idea in all the algorithms that we did for this thesis are the following. So we start on the leaves of this tree structure. We compute some solution to an associated problem, and then we move up successively every time using the solutions we computed below until we reach the root and we can give the final answer. Now, finally, we will see what's this framework of problems that I'm talking about. Actually, I will give a simplification of the full framework. The full formulation I will give at the end, so don't worry. But for now, this is enough to understand the main ideas of the results. So we're given a graph, and we also have a set of colors. So these colors are the ones we want to assign to the vertices. We also have this function, what we call a check function, which is simply a formalization of the local property. So this function is given a vertex and an assignment of colors to the neighbors of the vertex and the vertex itself. And we output true or false, depending on whether the local property is satisfied or not. Now, since we are also working with optimization problems, we are interested in having some notion of weights. So for every vertex and every color, we will have an associated weight. And we have an order of the weights. This is simply a technicality so that we can include both minimization and maximization problems in the same definition. Now, with all these elements, we want to find the minimum weight according to this order of an assignment of colors to vertices that satisfies the local property for every vertex in the graph. From now on, whenever I say coloring, I just mean an assignment of colors to vertices. So please don't confuse it with the problem of k-coloring. And well, the weight of the coloring will be simply the sum over all the weights in the whole graph. Let's see an example. Let's see minimum dominating set. So we can consider that we have two colors, So one color that represents the vertices that belong to a graph and another one that represents the rest. The local properties of the check function can be defined as true if and only if there exists some vertex in the closed neighborhood who's assigned the color that represents the vertices that belong to the set. We could have defined this function also in a different way, for example, like this. This really doesn't matter. As long as the function is well defined, it's fine. In this sense, this framework gives us more freedom than others, where we have, for example, to adapt something to a particular logic, while here it's just a function. So any way we define this is fine, as long as it's well defined. Next, well, we have the weights, which are quite trivial. It's 1 if the vertex is assigned the color in the set, 0 otherwise, and the order is like this because it's a minimization problem. So as we can see, it's quite intuitive to model problems in this framework because we simply need to extract the main elements of the problem and then put them here. So we need the set of colors, the local property, and the weights. That's it. We also included not only locally checkable properties, but we also allowed some concrete global properties. So, for example, we can ask that the number of neighbors of a certain color class is some number or an odd number, or we can ask that the vertices of some colors induce a connected or not connected subgraph, or even a cyclic or non-cyclic. And actually, we consider many more types of global properties for this thesis, but for now, I want to concentrate only in these 3 types. So we have size properties, connectivity properties, and cyclicity properties. Well, so what do we want to do? What's our goal with this framework? Well, we want to use this framework to obtain efficient algorithms for locally checkable problems when parameterized by treewidth, clique-width, and mim-width in this particular case. But we know already that there are some locally checkable problems that are actually NP hard even on trees. So we cannot solve just any locally checkable problem. We need to add some restrictions. We will study under which conditions we can actually achieve this. And the conditions will be on the set of colors and on the local property. And also we will analyze how can we extend this result with some global properties. Allow me now to start with the first restriction that we will put to the local property. So for that, I need to define partial neighborhood systems. Here's the formal definition, but let me go through it with some graphical representation. So imagine that we have a vertex V and its neighbors all already colored. Now, the idea is that instead of giving all this coloring at once to a check function, we will break it into neighbor by neighbor. So we will see neighbor by neighbor, and we will collect some information and then give it to some function. So for this, there's a function that creates information based on the neighbor and the color of this neighbor. And we will accumulate this information with this operator. And we will do this successively for every neighbor in any order until we reach the end. And with all the accumulated information, we will use this function to verify if the local property is satisfied or not. So in summary, this set NVI is a set of all possible values of the information we can accumulate. This function new is simply to create a new piece of information based on the neighbor, the color. This operator is to combine 2 pieces of information, and this function check-bi is well, to verify if with all the collected information the local property is satisfied or not. This equality that we ask here is simply to guarantee that the use of this tool set is equivalent to the use of the check function. Let's see an example. So let's see minimum dominating set. So here we can say that we will accumulate a Boolean value, either true or false, depending on whether we found the dominating neighbor or not. So when we create new information, this information will tell us if this vertex is dominating or not. We accumulate information with the logical or operator, and at the end, based on whether the vertex is in the dominating set or we found some dominating neighbor, we can answer finally if the vertex was dominated or not. So here, for example, we traverse the neighbors, we update the accumulated information, and then at the end, we can finally answer. In general, we can always give such a tool set for any local property, because we can simply take for every neighbor a pair, name of the neighbor, color that it gets. But the problem of this is that all the possible values that we can accumulate, all the possible possibilities that we can have, it's exponential. So we are actually interested in partial neighborhood systems where size of the accumulated information is polynomial, or so that the functions can be computed in polynomial time. And well, we also consider that we have constant, if these sets are constant. So for example, what we saw before for minimum dominating set, that was actually a constant partial neighborhood system because we had only two values, true or false. Well, moreover, we defined a universal partial neighborhood system, and this is simply when the first three elements here, they do not depend on B and I, which was actually the case for the previous example. Now, with all these definitions, we achieve these results. So we could give an algorithm using dynamic programming on the 3D composition of the graph that tells us that if we have a polynomial partial neighborhood system, a polynomial number of colors, then the problems are XP parameterized by treewidth. Actually, the same algorithm tells us that if the number of colors is constant and also the system is constant, then the complexity is actually FPT. For the other cases, for those groups of problems outside of these restrictions, here I write par-NP-hard, but actually this doesn't mean that all the problems there are hard. What it means is simply that there's at least one in each of these categories which is hard. So we cannot hope to give a generic algorithm to solve every problem in these categories. If we want to solve more problems, we would need to refine the set of restrictions. And what we have also an open case here, which I believe is hard, but we just need to find an example. Well, we also added some global properties. We could add size, connectivity, and acyclicity properties. For the parameter clique-width, we cannot simply extend the previous results because there are some problems which are par-NP-hard and have a constant number of colors and a constant partial neighborhood system, which is what before it was FPT, well, but now it's NP-hard. So we need to add more restrictions. So if we ask for now the partial neighborhood system to be universal, then we can indeed give an efficient algorithm for these cases. And we can also extend it with the global size of, with the global property of size. And we also still have some cases here. Now, let me present some restrictions that are actually easier than the partial neighborhood systems. Because even though it's quite powerful, it's still sometimes maybe not so intuitive when given a problem where it admits polynomial partial neighborhood system. So now these definitions will be more intuitive. So we say that the check function, so the local property, is color counting if it only depends on the vertex, the color of this vertex, and the number of neighbors that this vertex has of each color. For example, for minimum dominating set, we don't care exactly which neighbor has which color, or which neighbor is in the dominating set. We only need to count that there's at least one among the neighbors or itself. An equivalent definition for this is that, well, we can somehow rewrite this function so that the input is exactly the vertex, the color of the vertex, and the number of neighbors of each color. Maybe this is a bit more visual for minimum dominating set here. If we know the number of neighbors that are in the set, and those that are outside, just with this definition, we can verify the local property. And as it happens, these problems, those who have constant number of colors, a check function that is color counting, actually admit a polynomial universal partial neighborhood system. So only by checking if the function is color counting and that the number of colors is constant, we don't need to define anymore the partial neighborhood system. It's already given by this theorem. There's a similar definition where instead of counting all the neighbors of each color, we count only up to a certain constant d. So again, for minimum dominating set, we don't care if the vertex has 1, 2, or 700 neighbors in the dominating set. As long as it has at least 1, it's fine. So we only need to count up to 1. So what minimum dominating set is what we call one stable, because we count up to 1. If we count up to the constant d, that's what we call d stable. The set of LCP problems are actually d stable for some constant d, depending on the problem. So as you can see, this restriction, which maybe at first glance seems to be very restrictive, actually it's not at all like that, because this set of problems is quite large. It includes, well, what many of the, pretty much all the problems we know that are locally checkable, and so this includes that. And actually it includes even more problems. There are some problems that are not LCP and have a stable check function. And again, there's a similar result as before. So if we have constant number of colors and a stable function for some constant d, then this admits a constant universal partial neighborhood system. So again, we don't need to, in this case, the partial neighborhood system. And with the previous result, we know that these problems are repeated, parameterized like clique-width. Now, if instead of counting up to d, we count modulo some constant, for example, in the case of minimum dominating set, well, the results are similar. So we also have a constant partial neighborhood system. So here's a summary of this that I was talking before. These results, actually, they were published before in an earlier version together with Narmina Bagirova, David Schindel, and Bernard Rees. And in this article, we gave a specific algorithm for these restrictions. But now, with this generalization presented in the thesis, the partial neighborhood system, this is simply a corollary. Let's see an example so that we can understand this better. Let's think of a problem called Roman K domination. So in this problem, we want to find the minimum weight of a function that assigns numbers from 0 to k to the vertices, such that every vertex that gets the color 0, sorry, the number 0, the sum of all the neighbors is at least k. So first of all, is this problem locally checkable? Well, yes, because it's a coloring or partitioning problem, as we can see here, where some local property needs to be satisfied, because this only depends on the vertex and the neighbors. So yes, it is. So we can model it within our framework. And so let's start. Let's see, the set of colors is simply the numbers from 0 to k, as is said here. The local property, the check function, but it's simply like this. If the color is 0, then the sum of the neighbors has to be at least k. It looks like a copy-paste, basically, of the definition, which is actually that, because we are simply, as I said before, extracting the main elements of the problem. The weights are simply the values that we assign to these vertices, and the order is like this because it's a minimization problem. Notice now that, well, we have k+1 colors, so constant number of colors, and that the check function is color counting, because if we know how many neighbors we have of each color, that's enough to compute the sum. So we can rewrite it like this. And actually, not only color counting, but it's also k-stable, because if we have more than k neighbors of some color, then this some array saturates, or well, or if they had value 0, they would actually we don't care. So now, since we know that the problem has constant number of colors, and in this case they go for some constant, using the previous results, we can already answer this problem is FPT parameterized by clique. Now for mim-width, we also did some study together with Felix Mann. We obtained that for problems that have a constant number of colors and a d-stable check function, these problems are XP parameterized by the mim-width of the given decomposition. For the previous results, we didn't need to be given the decomposition because there are some algorithms that gives us a nice approximation for that, but not for treewidth. So we'll still need to ask for the decomposition to be given. And as you can see, the panorama for the others, for the other cases, is much darker. Everything seems to be hard here, well, with the exception of these cases, which we also believe that are hard. And well, so for the case that we can actually solve efficiently, we also included global properties of size and connectivity. We can actually include another property, which is the cyclicity property, but not with the algorithm we gave. Instead, this is through another framework. It's the framework, if you remember, that I mentioned in the beginning, ANCDN logic. So this logic was defined by Bergogneau, Dreyer, and Jafke in 2022. So more or less at the same time when we were studying those problems. And basically they proved that every problem that is expressible in this logic can be solved in XP time parameterized by the mim-width of a given decomposition. And as it happens, actually, problems that can be modeled in this logic and the problems that we can model with our framework using global properties of size, connectivity, and cyclicity, and well, in the full formulation where we also include distances, which I didn't present here, these two sets are equivalent. So we proved translations from one to the other. And using these translations, we can actually include cyclicity properties for our framework. We can use this algorithm to include them. But what happens sometimes is that, well, it might be more efficient to model directly the problem in the other logic than using this translation. Because with these translations, it is very general, we lose some complexity there. However, if we don't have cyclicity properties, then it's usually more convenient to use our framework. But the complexities are actually quite similar because, well, it might seem surprising actually that these two frameworks of completely different nature are well, obtain the same results, basically. But actually, since they are both based on the same algorithm, which is an algorithm for LCP problems using branch decomposition, then it's not so surprising anymore that we obtain pretty much the same result because we are extending the same algorithm. Now, allow me to talk about a completely different problem. So now we finished with all the exact results. So let me show you approximation results that we obtained. So first, I need to define what's the polynomial time approximation scheme. So basically, this is an algorithm that, given some epsilon, it returns an approximate solution that is not too far from the optima. It's within a rate of 1 plus epsilon for minimization problems and 1 minus epsilon for maximization problems. And the complexity of this algorithm has to be polynomial for every fixed epsilon. This is very powerful because it allows us to get as close as we want from the optimal value. However, then we have an impact in complexity. The closer we want to get to the optimal value, the more time it will take us to compute it. But still, it can have some applications in real life. And there's a very famous technique called the Baker's technique, which is to obtain polynomial time approximation schemes on planar graphs. It basically works like this. So we have a planar representation of the graph. We fix some k, which will denote how close we want to get to the solution. In this case, the larger the k, the closer we get to the solution. And so now the idea is to divide this representation into different layers in such a way that the treewidth of each layer only depends on k. Now on each layer, we will solve some associated problem, where the idea is that this problem is xp parameterized by treewidth. And then we have to define how we combine these solutions. The solutions here are exact, and now we combine them into an approximate solution of the original problem. And now if we carefully choose how we take the layers, which ones are the associated problems that we solve, and the combination algorithm, then we should obtain an approximation rate that only depends on k, and an overall complexity which is xp parameterized by k. And this is what we did for some locally checkable problems. So we build on the restrictions that we had for obtaining XP algorithms parameterized by treewidth, and we create some more that depend on the combination algorithm. And now I will not define the exact conditions that we included. I will just give the rough idea due to lack of time. So the idea is to have some sort of set of colors. So these colors, the idea is that they never make a solution valid. They can make it worse in terms of the weight, but it will not break it, say. So for example, for minimum dominating set, the color that represents the vertices in the set is a safe color, because if we add more vertices to the set, we can never make it undominating. We just make it large. Well, not every problem admits such a set, as we can see here. But since many domination-like problems are actually hard on planar graphs, and they actually admit these safe colors, this is a very interesting result. Now, well, finally, to conclude, let me present you here the full framework. So here we included larger distances. Yes. So not only the neighbors that are the direct neighbors of the vertices, but also those vertices that can be up to a distance r. The vertex, we also allow to have some set or list of permitted colors for the vertex. This is similar to list coloring. We also have edge labels where we can put the distances and other information. We also have a more general weight function that depends not only on the color of the vertex, but on the color of the neighbors. And we also included more global properties. We included completely this one called local condition composition, which is inspired in the framework of the same name by Botlander. And it's a very powerful global property because it includes as well, well, first the size global property can be modeled with this one. We can also, for example, count edges in a particular color class. And it also, as a curiosity, it generalizes the check function. However, we want to keep it separate so that it's more simple to understand. One thing is local property, another one is global property that just happens to generalize this. But it's useful still because, for example, we can say that, well, maybe we don't want the local property to be satisfied for all the vertices. Maybe we want, say, 80% of the vertices to satisfy a local property. Well, we can model that with this global property. Here's a little summary of the minimum conditions that we need to impose to the problems so that they can be solved in XP time, parameterized by different width parameters. We actually consider another parameter called carving width. And well, all these results happen to generalize the results obtained for LCC, ECC, and LCP problems. And as I mentioned before, the results for mim-width completely, they are almost equivalent to those obtained for ANC and logic. And actually here there's yet another difference because we could also manage to model, to include with our algorithm the global property of local condition composition. And we don't know yet if this property can be modeled in the logic. So this can be yet another difference. And well, finally, we also included approximation algorithms for some of these problems on planar graphs. And here we can see a very a very large set of problems, but this is actually just a selection of some problems that already existed in the literature and that we knew that their complexity on these graph classes was unknown. So now, by simply modeling these problems in our framework and analyzing which restrictions they satisfy, we can directly answer that. And well, some of them actually also admit polynomial time approximation schemes on planar graphs. And well, to conclude now, so let me mention some open questions. So as you saw before, we had some question marks on the table. So all these cases are open. I believe actually that all these cases are apparently hard. We just need to find some examples of problems there that we can prove that are hard. In particular, the question mark that was on mim-width about problems with constant number of colors and n-modular functions. We are interested in that one. We don't know what happens even for the problem of minimum or dominating set on proper integral graphs. So that can be some nice starting point for answering that question. Then, well, we can also try to answer if we can give more polynomial time approximation schemes or more graph classes. In this direction, there's, for example, an article by Esther Galvi and Andrea Munano, where they define some methods similar to Baker's technique, but the layers there, instead of having bounded treewidth, they have bounded mim-width. So since we know how to solve problems on bounded mim-width graph classes, then this could also be the direction to continue. We have some problems for which we prove that they are XP parameterized by treewidth, but we don't know whether they are SPT or not. So it would be nice some results of either giving a more efficient algorithm or proving that they are double hard. And finally, well, we can also consider more width parameters. There are many new parameters defined recently which look promising for doing some similar analysis to this one. And well, thank you very much for your attention. Now I will answer any questions that you have. Thank you.
Dimitrios, do you want to start?
Sí, puedo
Yes,
empezar
please,
yo,
go ahead.
pero ¿lo hago en inglés, lo hago en español?
Como
Así.
prefieras. Es que uno de los jurados había pedido en inglés, si podía ser,
Inglés.
por eso Carolina
Inglés.
hizo la presentación en inglés, pero
Ok.
como te resulte más cómodo, no hay ningún problema.
Sí.
Demetrius, I would prefer if you speak English so that I don't ask same questions afterwards.
Okay.
Sorry, give me just a second. I will close the door.
Yes, close the door, please. Yeah.
Thanks a lot for the nice presentation. It was very, very representative of the results. So you gave a very, very good flavor about the results and their originality. So somehow you made some real brave effort to push this as much as possible. And so one question is, I mean, for me, the most surprising thing is this equivalence that you prove between this combinatorial formulation and the logical formulation that appeared recently. So somehow, to what extent do you think that your way of doing things can go even further? This is one question.
The sound is so good that I don't hear the question.
Is it clear?
And the volume.
I'm trying to adjust the volume, but
It's at maximum, sorry.
Yes.
Maybe can you speak closer to the microphone?
Yes, I have a microphone here. So the question is,
Yes.
I mean, for me, the most impressive result
Mhm.
I mean, what really was an impact? I mean, it was that the framework that you developed, which is building on previous framework, but you really push it very far away, is equivalent in a sense with the framework, with the logical framework existing.
Yes.
So my question is, can you do more than this? I mean, do
Proving
you really
that.
believe that your framework has better potential? I mean, there are some kind of clicks that we can push it further.
So specifically about this ANCD and logic. So in this direction, for example, well, there's this global property of local condition composition that we don't know if this can be expressed in ANCD and logic. So maybe this is the more general, this might include more problems. Of course, we cannot handle acyclicity. So if we wanted to actually be more general than those results, we would need to also include acyclicity. But since both papers are actually based on the same algorithm, I think this is possible to include acyclicity as well in our algorithm. But as well, it might be possible to somehow extend the logic to include local condition composition. With respect to other logics, so for example, with monadic second order logic, no, we didn't analyze if one is more powerful than the other. So for our framework, on one hand, it gives us also XP algorithms, which is something that Husserl's theorem doesn't, because it's only for FPT problems. But we didn't analyze if all the problems that can be modeled in logic can actually be modeled in my framework. I believe that that's not possible actually, because Husserl is much more general than just locally checkable. So maybe we could, but we would need to add many more global properties specifically for that.
Okay, I have one more question. The next.
Hello?
Now we lost you, Dimitrios. We don't hear you at all.
Yes, we lost you.
I now
mean-
press the correct button. Okay, my question is whether you can add parity constraints in your dynamic programming framework.
Well, for some of the results, yes, actually. So we have this condition of immodularity, so that can actually include parity constraints. And as we mentioned here, so that problems that have an immodular function, so for example, 2 modular could be something with parity. That is considered for clique-width, for example, and also for treewidth. But we don't know whether we can actually include, sorry, but I can include that. So I can. No, just, yeah, okay, thank you. So that for mim-width, actually it's open. We don't know whether we can solve in XP time. As I said, even minimum odd dominating set, we don't know if we can solve it for interval graphs. So your request, to answer your question, yes, partially. So for some parameters we can include parity. For some others, we don't know. I believe not, actually. I know that we. Sorry.
Yeah, I'm very happy with the answer. This is what I want to comment.
Oh, thank you.
Should I take over? Yeah, I also enjoyed very much the presentation, and I actually enjoyed very much reading the thesis.
Thank you.
So just one parenthesis, for some reason your camera is gone. Now I cannot.
Yes. Can you hear me?
I can hear you, yes, but I cannot see you.
Yes,
Should
yes,
I?
turn off, Carolina.
Should I continue without the camera or should I wait?
Give her 1 minute.
Yeah, of course.
If she can just fix the small issue.
Yeah, there are always this technical.
Okay, we lost her
Yes.
completely. I think she went for the restart option. Yeah, just restart Zoom client to fix everything.
Ya volverá.
Ya volverá. Así es.
Yeah, it's no problem.
Paloma, one question regarding the administrative process. We have to complete a formal document. Your nationality is Brazilian?
Yes. And the name of my university, I'm not sure it's
No,
correct.
I only need your place of
Nationality.
birth. Yes, only
Okay.
that. The rest of data is in your CV. Everything's okay.
Okay.
I'm gonna run downstairs to see what is happening in the classroom. Give me 1 second.
Okay.
Hope it's not some kind of accident.
Yeah. Yeah.
Like, for example, the computer fell down or something like this, right? That's
Oh my, let's hope it's not
Yeah,
this
yeah.
tragic.
They're trying to initiate it.
we should be careful with jokes we make because we are in YouTube, but
Oh, okay. Oh, now we're back.
Hello, we had a
Hola, ya os vemos, ya os vemos.
some technical problem. Now we have the network, right? Basically, we're using now some mobile data. So
Oh,
okay, sorry. So it's connected with this now. Can you hear me? Wait. So, yes, well, actually, I'm going to maybe move the camera, just change the camera. So we use the one in the. I will just continue with this camera, with the one in the computer. Okay? Right.
Yeah.
So let me share the slides again. So yeah, sorry for the problems.
it's no problem at all with online things. There is always this variable in the game. So are you ready? Should I continue?
Yes, please.
Okay. So actually, my first question, I will maybe go backwards, is about the open problems you mentioned. Because, so you mentioned obtaining, let's say, analogous types of results for order with parameters. And of these parameters that you included there on the slides, 3 of them generalize cordon graphs. Right, sim-width, one-sided mim-width, and tree independence number. And one of your toy problems, which is dominating set, is NP hard on cordon. Right, so what kind of, so this, whatever restrictions you define to get algorithms, they have to go around with the fact that you should not be able to express dominating sets, which it looks like a major problem. So I wanted to ask, what's your plan for that?
Yeah, it is. So we don't have any specific action plan for that. What I would do in this case, because we know that we can solve independent set, for example, for one-sided mim-width, I think there's an algorithm for independent set. And then for some graph classes, we know also for coloring problems. So my way to attack this issue would be, well, first study all the algorithms that we know for these parameters, and then maybe try to extract some generality out of them. See what the main idea behind why these algorithms work for these problems, and what makes these locally checkable problems that are solved, they are actually solvable. So yes, it's quite hard to separate minimum dominating set from maximum independent set, because they both have two colors, and the only difference is that one is minimization, the other one maximization. Well, and of course the local property, but they're very similar.
It's one
But
stable.
for example, for obtaining polynomial time approximation schemes, there we had to separate coloring from the other kinds of problems.
Exactly.
So that seems hard, but I'm not sure it's impossible. I think there must be some way. Of course, yes, it will be very hard to do that. So other parameters are more promising. So tree independence number or treewidth look more promising for them. But it would be really, really interesting to see why dominating set is hard, but independence is easy. So how we can separate those ones, that would be very interesting. Of course, as you mentioned, very hard, but very interesting.
Right. All right. So one other thing is that so there are many coloring problems that are XP by clique-width when the number of colors is unbounded. Right, so this is the case for normal proper coloring, is the case for B coloring, and I think there are some other examples. Does coloring with unbounded number of colors fit somewhere in your, like in the table entries that you have, like this one, for instance?
Yes, so actually for problems with unbounded number of colors, either we found some NP-hard results or no results at all.
Yeah.
So actually for the parameter carving width, which is the most permissive one, because they are the local function is just any function as long as it's computable in polynomial time. But actually then the number of colors has to be bounded by some polynomial. If it's unbounded, then we can already find some examples of hard problems, even for carving width, which is a very, very limited parameter. It's like binary trees classes. So having unbounded number of colors is actually a sign that the problem might be hard. We don't have any positive results on that side, but it would be also interesting to analyze if we can actually manage for, even for some graph class or for some restrictions on the local property, where we can unbounded number of colors.
Yeah, because I think there are many like single results of this type, which are actually algorithms.
Very ad hoc problem, exactly, yes.
Exactly, and there is no like common explanation for that, as far as I know. So that would be interesting to have. But one thing that all these algorithms have in common, or at least all the ones I'm aware of here, is that instead of looking at the definition of clique-width, they use an equivalent parameter that is called modulo width, which is not modular width, it's another thing. So it's a module width, which is also based on branch decompositions.
Exactly, yes.
So that could be like a way for you to approach this. And actually,
we did not actually analyze that. For clique-width, we used the definition of clique-width, so the one with the labels We didn't use the branch decompositions, but that can certainly be another way to continue.
Yeah, so I also made a small comment to tell you that I think maybe some of the results can even be made easier if you use module width instead of clique-width. I at least find a lot more intuitive. And it has to do with those neighborhoods equivalence classes. So I think it's an interesting thing to look into.
Very nice. Thank you for the suggestion. Probably the algorithm will look more similar to the one for mim-width. Very nice. And it's actually more useful for considering more parameters. So if we study this branch decompositions, then certainly. Thank you.
Right. So one thing that I must say I really liked about your presentation compared to your thesis is that I think you put a lot of way more effort into making some things more intuitive, right? And the one thing that all these like logical frameworks and these frameworks in general have as a problem, in my opinion, is that you have these people that actually really understand it, and you have people that have absolutely zero intuition about it, right? So I still get many papers that are solving problems on interval graphs, on permutation graphs, and when I look at the problems, I clearly see that they can be expressed in this AC and DN logic. So, and these is of course not even mentioned in these papers. So I think it's important to try to make these things a little bit more accessible to people in your publications, as well as, I mean, in the presentations, it's always easy because we do these working examples that really bring the intuition. But I think it's maybe important to do that in writing as well, right? And okay, and then my question is actually that, so you mentioned in the treewidth paper, the first in chapter 3 or something like this, so that there are some problems that they now fit this framework and that they were not known to fit the locally checkable framework that was there before. Right, this Grundy domination is one example that you give, and this k-Roman domination as well. And then I wanted to ask if you see any common characteristic in these new problems that now fit your framework and before they were not there. So for instance, if I get a problem to solve now, and is there some property that should ring a bell to me, like, oh, I think this is a type of locally checkable problem that now fits this framework?
Yes, so for example, in comparison to LCVP problems, in that framework, the conditions somehow handle the color separately. So it's something like I need to have some certain number of neighbors of a certain color. Also, separately, some other number of neighbors of another color. But so the colors are handled independently. They are not combined. So for example, for k-Roman domination, what's important there is that the sum of the neighbors has to be some value. So that's something that for me, it's, yes, these kind of problems where we have to combine now the conditions in the neighbors, it's something that we couldn't do, for example, with LCP problems, but now we can handle here because we can combine these restrictions.
Right.
So, well, and that would be, for me, the easiest framework to compare with the other ones that are much more complicated. I'm not sure I get the intuition very quickly of the other frameworks. Yeah. I would need to see.
Yeah,
but
I completely agree that. I completely agree that providing intuition in there is a difficult task. It's not trivial. But I think this observation that you just made is it's very interesting. Okay, so maybe I have just one more question and then I pass on, which is, so for our locally checkable problems, you assume you get like on graphs of bounded carving width, but basically because you use bounded degree to ensure that the power of the graph will have bounded treewidth, right? Can this condition on bounded degree be removed if you consider a different approach, or is there some problem that shows that it wouldn't be possible to?
Yes, thank you. It's a very nice question. Actually, yes, we consider that for some problems where, for example, the distance does not involve distance within the same color. So, for example, say we have the vertices need to be a distance at most 1 from from the vertex of color red. If they get, for example, well, or actually no, 1 no, actually my larger distance, sorry. So asking between 2 different colors, it's fine because we can like exploit the number of colors so that now we indicate also how far they are from another color. So then we can say, well, okay, a vertex gets a color which is like example 1, 2, 3. If it's a distance 1 from a vertex of color red, 2 from a green one, 3 from a blue one. So if this distance have to involve 2 different kinds of colors, it's fine. If they are within the same color, then that's a problem.
I see.
But for the others, yes, because we can just enlarge the set of colors and then we can include more. Of course, the distance will have to be well reasonable depending on the type of result we want. The distance will have to be constant or whatever, it can be polynomial depending on the case we have. That for treewidth.
I see. All right. Thank you again for the presentation. I really enjoyed it and I had a nice time reading your thesis, learned a few new things. So thank you.
Thank you, and thank you for your suggestions.
Thank you, Paloma. I think the next one is Sergio. Sergio.
Thanks very much. As Dimitrios and Paloma said, the presentation was really nice. Thank you. As they say, it's easier to give a nice presentation once you have nice results as you do. So that is the first step to give a nice presentation, to have nice results. That simplifies life a lot usually. I have a couple of questions, so the first one is, I like, when I was looking into the thesis, I like this concept of locally checkable things mixed with global properties. Like, for example, you're talking about connectivity. It's one of the global properties you mentioned. And I was wondering, can you handle also like 2 connectivity? Is this an option? Because connectivity is way easier than 2 connectivity.
Yes, honestly, we did not think about it. We will have to analyze it. I guess maybe for treewidth, yes. Treewidth seems like a very easy parameter, maybe not so easy for the rest. I will need to analyze it. Honestly, we did not think about it. But it's a very nice connectivity, property to consider to extend these results.
And also connected to global properties. I was also wondering, for example, so let's say you're looking at independent sets with errors. Like you tell, I want the largest set of vertices that half of them will be independent, meaning half of them should not have any neighbor in the set. Is this something that can be handled also in this framework, or?
Yes, I think we can handle that with the local condition composition, because this one generalizes the check function. And as I mentioned before, we can ask for a particular number of or proportion of vertices that satisfy some condition, and we can add as many as we like. Well, not any number, of course, not an exponential number of conditions, but we can also add another one that says the opposite. That, well, some proportion of the vertices don't satisfy this property. Yeah, we can make use of this global property for that.
Okay. And then the other question I have is about Baker's technique. So somehow that's a chapter that, well, you said, I mean, it's not published. It comes still, it looks a little bit more work in progress than the others, which are very worked out, let's say. So there are, I mean, Baker's technique, there are extensions, one of them for graphs on surfaces. There are also extensions of Baker's technique for contractions. So did you look into any of these directions? In particular, contractions. I mean, for problems when you contract certain subgraphs, the optimum doesn't increase or doesn't decrease or something like this.
No, honestly, we did not look at this yet. This is a very new result. Actually, it was it started as a suggestion of a professor here in the University of Michelin. He had a student working also on Baker's technique on other problems, and she said, well, it would be nice if you could do that for local checkable. And so I encouraged that, but I didn't go further with this. But it would certainly, yes, be interesting to consider. Not only the extension that I mentioned, which is one that I just happened to see because I know the authors, but also these other ones that, yeah.
Because, for example, the edge deletion that is using Baker's technique, that, for example, will not go good with connectivity. Which is what we were. I mean, so once you delete edges, you cannot keep track of connectivity anymore.
Well, actually, in the results that are in the thesis, we don't consider global properties for this. This is purely local. Just the starting point for studying this kind of results.
Okay. And otherwise, I was planning to ask to talk a little bit about this boundary between what problems are solvable and which ones not. But I mean, through the presentation, you did an excellent work about this already. So I think the question is pointless now. So thank you very much for the presentation and the work. It has been a pleasure.
Thank you very much. Also, thank you for the suggestions. We consider them for future work. Well, so, if anyone in the field has questions, I didn't receive any, so I guess someone in the public maybe has questions. No, okay, well, then I guess that's it then.
Well, I think everyone has fulfilled all your doubts, your questions. Paloma, do you have anything else to question, Dimitrios?
No.
Good.
We are done? Okay. So, Flavia, you should just leave the classroom empty, and I'm gonna start the breakout room to invite the reviewers, and then
Okay.
we have to wait. You have to wait outside the room.
Okay. Okay.
I'm gonna check now if you are outside.
Okay. Okay. Okay.
We are very serious in this.
Yes.